Good day, everyone. My name is Nonya, and I will be the first reporter to report about the first two eons of the Precambrian, the Hadean Eon and the Archean Eon. You may be wondering how the universe or the Earth started to form, so here is a look back to the Earth's earliest history. The Hadean Eon. During Hadean time, the solar system was forming probably within a large cloud of gas and dust around the Sun, called an accretion disk. The relative abundance of heavier elements in the solar system suggests that this gas and dust was derived from a supernova or the explosion of an old massive star. Hadean was named after the god of the underworld Hades, a Greek translation of Hebrew word for hell, and it was the oldest eon. This time represents Earth's earliest history, during which the planet was characterized by partially molten surface, volcanism, and asteroid impacts. Several mechanisms made the newly forming Earth incredibly hot: gravitational compression, radioactive decay, and asteroid impacts. Most of this initial heat still exists inside the Earth. The Hadean was originally defined as the birth of the planet occurring 4.0 billion years ago and preceding to the existence of many rocks and life forms. What are the evidences that proves the occurrence of Hadean Eon? The late heavy bombardment. The Hadean is described as hell on Earth due to the late heavy bombardment. LHB is a theory that the entire inner solar system suffered through an intense spike in the asteroid bombardment roughly 4 billion years ago. The theory grew from studies of the Moon's crater record and the hundreds of kilograms of lunar material returned to Earth by the Apollo astronauts. The history of the late heavy bombardment. Throughout most of human history, the moon was thought of a partner to the sun, dimmer but still a symbol of heavenly perfection. Galileo received quite a shock 400 years ago when he turned his newly built telescope to the moon and discovered that its surface was pockmarked with circular craters. The circular scars on the moon are impact craters made by the violent collision of asteroids and comets with the moon. In 1960, geologist named Eugene Shoemaker published a doctoral thesis on meteor craters in Arizona. He believed that the meteor craters and moon craters had an impact origin. When Shoemaker examined the rocks near the explosion sites where he worked, he discovered new minerals and rock textures that had been created by the high shock pressures and low temperatures of the nuclear blast. And Shoemaker found some of those minerals as well as in meteor craters. These minerals are never found in even the most violent volcanoes, where temperatures are high but pressures are relatively low. The minerals and textures Shoemaker discovered allowed geologists to tell volcanic craters from impact craters and eventually led to the understanding that the moon's craters mostly form from impacts, though a few definitely are volcanic. But why did the Earth was included in the asteroid bombardment? Earth and the Moon occupy the same position in the solar system, so they must have the same flux of asteroids, but Earth bears many fewer craters than the Moon. That's because Earth's active geology wipes its surface clean of the violence of impact craters. This violent period in the Moon's history is now called the Late Heavy Bombardment. Controversy of the Late Heavy Bombardment hypothesis. Historically, astrogeologists have had three main objections to the idea. One is the question of how you could form a nice peaceful solar system and then somehow, long after the solar system formed, you could suddenly send a huge bolts of asteroids or comets to bombard the planets. Number 2. Where were all of those impactors hanging out for the 600 million years? And 3. What could possibly have caused them to suddenly change their orbits to Earth-crossing ones? This objection has recently been answered by the Gneiss model. It is a model in physics terms and a set of mathematical rules that can be used to predict the behavior of a physical system. It was originally written down to attempt to explain some oddities about how Uranus and Neptune form. They figured out that Uranus and Neptune likely formed much closer to the Sun, and as they interacted gravitationally with Jupiter and Saturn, they were kicked outward into a disk of icy planetesimals. This outward migration sent millions of comets towards the inner solar system, bombarding the planets and also disrupting the asteroid belt, which bombarded the planets some more. The Gneiss model can't predict when this happened, but it can be tuned with reasonable choices of starting condition to force the event to happen at the right time, 600 million years ago. So there is now an explanation for how it would have been possible for impactors to wait around for 600 million years before causing the bombardment.
Hello, I'm Bonner Gaspina, and to continue, I will present a few more evidences that supports the geological information of the Hadean Eon. So, the Hadean Eon was said to be hellish and that the Earth was very hot and molten, and this is because of the three main contributing factors. And these are the impacts of the bombardment, the gravitational compression, and the radioactive decay of isotopes such as potassium, thorium, and uranium. Meteorite impacts heated up the planet's surface areas via shock waves and impact melts. And the gravitational potential energy is converted to heat during that compaction. Because when an object falls from a height, in this case a meteorite, it converts gravitational potential energy into kinetic energy. And when that meteorite hits the surface of the Earth, which stops its fall, all of its kinetic energy is converted into heat added more than to what it had to begin with. Now, however, the heat generation decreased over time because the abundance of radioactive elements diminished due to decay.
It was stated that the gravity of the Earth in the Hadean times could crush a human body flat. What does this mean? That means that the gravitational force is so strong, pulling the body to the ground and the organs will crush. The blood will flow back to the feet and humans and other beings cannot survive. The high gravity could also cause or add up heat since the gravity pulls creating pressure and so pressure creates heat.
Next we have is the presence of siderophile elements on Earth. The late heavy bombardment helped adding more siderophile elements into the mantle and crust, as most of the Earth's original siderophile elements had been sequestered in the core. Example of siderophile elements are gold and platinum. By the way, siderophile means iron-loving elements. Now, the meteor or the asteroid impacts delivered a percentage of the planet's total mass. Many space debris, such as meteorites that fell into the Earth, are analyzed and said to have or contain a relatively high amount of highly siderophile elements, or HSE. This indicates that the meteorites that hit the Earth carried an ample amount of siderophile elements. Ancient rocks in Isua in Greenland date back to more than 3.8 billion years ago, and like the ancient Greenland crusts, these rocks have tungstens, a slightly less iron-loving element, or a siderophile element. Now, according to Chris Dale, a postdoctoral researcher, the presence of the iron-loving elements outside the core suggests that they were deposited there by impacts with other bodies. Therefore, the addition of siderophile elements could have been caused by the late heavy bombardment or LHB, since meteorites that fell into the Earth are repositories of siderophile elements. Then here we have the Isua Greenstone Belt. I have mentioned the rocks in Isua or the Isua Greenstone Belt earlier, and it is one of the evidences of the Hadean Eon. According to a study, it is an Archean greenstone belt in West Greenland aged between 3.7 and 3.8 billion years. However, according to Rollinson, the Isua Greenstone Belt is a metamorphic rock or a metamorphically altered rock. Hence, the protoliths or the type of rock that metamorphic rock used to be prior to metamorphism before being derived must therefore predate the rocks, essentially making the Isua Greenstone Belt older than recorded, possibly between the transition from Hadean to Archean Eon. Now, let's jump on another rock and proceed to the Acasta Gneiss in Canada. The Acasta Gneiss is the Earth's oldest known rock and is the first evidence of stable crust. Stern and Bleecker suggested in their study that this oldest known continental crust is even older than previously thought, supporting the premise that the composition and texture of the Acasta Gneiss indicates that Before metamorphism, the gneiss was an igneous rock that formed about 4.03 billion years ago, and this age is determined through the service geochronology laboratory isotopic dating. Sorry, I messed up. And that's pretty much it for the Acasta Gneiss. Let's move on to the zircons found in Jack Hills, Australia. Researchers have found zircons up to 4.4 billion years old under the Hadean Eon, and the zircons that were discovered have to have been part of the early crust, because the zircon crystals that were measured are detrital, meaning a product of disintegration, destruction, or wearing away. Therefore, according to Dr. White, they were weathered out of the pre-existing rock, and essentially that rock has to be exposed out in the atmosphere, and if it is exposed in the atmosphere, it has to be part of the crust. And next we have the formation of ocean. After the zircons in Jack Hills were analyzed, the researchers found out that the amount of oxygen 18 in the zircon crystals was higher than expected. And typically, a crystal that has higher oxygen 18 concentration indicates strongly that these zircons have come into contact with cold water on the surface of the Earth. When minerals interact with surface water, it causes the oxygen isotope ratio to change. The interaction will increase the amount of oxygen 18 in the mineral, hence the increase in the oxygen isotope ratio in the aforementioned zircon.
In Hadean Eon, the ocean was said to be iron-rich. The atmosphere of the early Earth is poorly known, but it is thought to have been smothered in the reducing gases containing very little free oxygen. The young planet had a reddish tint, and its seas were thought to be olive green. Many materials with insoluble oxides appeared to have been present in the ocean for hundreds of millions of years after the Earth's formation. Classic models for this time window maintain that the ocean, all depths, became rich in oxygen in parallel with its first accumulation in the atmosphere.
And now we're down to the last part of the report, the life in the Hadean Eon. According to a web article written by Julia Rose, a science journalist, the mere presence of the minerals does not prove biology existed when the zircons formed, but it does provide the opportunity to look for chemical signs of life. The researcher Elizabeth Bell and her team found a small bits of potentially undisturbed graphite in one of the 4.1 billion year old zircon crystal. The graphite has a low ratio of heavy to light carbon atoms called isotopes, consistent with the isotopic signature of organic matter. According to Bell, that carbon would be biogenic, or a substance that is a product made by or of life forms. Added by the existence of liquid water at 4.4 billion years ago, it could have important implications for the evolution of life. However, there are no clear evidence that life really did begin in the Hadean Eon, since the microfossils that were found were as old as 3.5 billion years. Although it does suggest that the Earth by this time is much more milder and amenable to life. And that ends our presentation for the Hadean Eon. Let us proceed with the Archean Eon.
Good evening, everyone. We will now discuss the Archean Eon and some of its evidence. Archean comes from the Greek word arche, which means beginning or origin. It is the second of four geologic eons of the Earth's history, representing the time from 4,000 to 2,500 million years ago. In this time, the Earth's crust had cooled enough for continents to form and for the earliest known life to start. Life was simple throughout the Archean, mostly represented by shallow water microbial mats called stromatolites, and the atmosphere lacked free oxygen. So these stromatolites, these are the oldest known fossils, representing the beginning of life on Earth, and is one of the evidence that was found that proves the occurrence of Archean life. The first evidence was found in the Dresser Formation. Some of the Earth's earliest convincing evidence of life is from the Dresser Formation, which had been interpreted as a marine environment. However, recent evidence indicates that the Dresser Formation was deposited within a volcanic caldera affected by voluminous hydrothermal fluid circulation, The Dresser Formation is located in the Pilbara region of Western Australia. In here, the researchers have found exceptionally preserved organic matter inside samples of rock. The formation contains samples of sedimentary rock from the Paleo-Archean era, and inside the rocks, it contains layered structures called stromatolites. These are known to form when microbes grow into thin layers, which then become covered in sediments, only for another layer of microbes to form on top, and so forth.
Evidences: Dixon Island Formation. Field observation and geochemical evidences suggest that this formation contains a low-temperature hydrothermal vent system with a biogenic microbial colony from the Archean Ocean. The Dixon Island Formation is -300 m thick and consists of the rhyolite tuff, black chert, and varicolored chert members. In ascending order, the rhyolite tuff member contains many vein swarms, such as quartz and black chert veins, and highly altered rhyolite tuff layers, which are identified as an underground bypass zone for circulating hydrothermal fluid. The ball assemblage, comprised of dominantly alkaline mafic to felsic volcanic sequence with minor comatite, siliceous, clastic, and stromatolitic carbonates. These 200 m thick stromatolitic carbonates are the eastern extension of the Red Lake Wallace Lake Carbonate platform in the Red Lake area. From 4.6 to 4.0 billion years ago, the Hadean Eon was a violent time in Earth geologic history, but in the Archean Eon, Earth finally started to cool down with a more stable climate. So some of the major highlights of the Archean Eon include ocean and continents. Because Earth cooled down, it was able to support ocean and continents. Banded iron formation. Next, oxygen filled the oceans from the cyanobacteria. Interestingly, most of the world iron ore deposits were produced in the Eon banded iron formation. Low ozone layer. Eventually, the ozone layer forms. This layer protection was essential for the life to form.
Hello everyone, so this time I'm gonna discuss more about what is on the Archean Eon. The first tectonic activity builds up the continents, and then the oxygen begins to fill the atmosphere. So this time nga nag-start pa lang ang Archean Eon na mga events sa Earth nga nag-create og kanang earthquake, and then it created the what they call supercontinent, but there is no later discussion on the topic. And then the iron collects on the seafloor as oxygen filled the oceans. Naay mga microorganisms nga nagbloom ani nga mga panahon na, and then there are called the cyanobacteria, in which nga sila ang responsible nga nag-create og oxygen sa seafloor. Mo nang matingala ta nga about sa history nga nganong magsugod or nganong dadto gyud kasugod ang life, kay it's because ang oxygen at that time kay nag-overwhelm sa seafloor is because of the cyanobacteria releasing the oxygen into the ocean. So this time around on the Archean Eon, most of the rocks which survived are volcanic or igneous and metamorphic in origin. So volcanic or mga magmatic rock nga ginaproduce sa volcano each time nga mag-erupt sila. So volcanic activity was everywhere when the Archean began. The Earth's heat flows was nearly 3 times higher than it is today. Obviously, it's because of the volcanic eruptions nga nag add up sa kainit sa Earth. And then the large supercontinent Valbara formed in the Archean. So after the eruption, paguman og kanang erupt sa volcano, nag-create siya og isa ka supercontinent that is called Valbara. And then there were oceans already before the Archean. The atmosphere almost entirely lacked of free oxygen, and instead it was mostly methane and carbon dioxide. The landscapes that are formed during this eon. The Pilbara is a large, dry, thinly populated region in the north of Western Australia. It is known for its Aboriginal peoples or mga tao nga dugay na kay namuyo didto, and its ancient landscape. The the red earth and its vast mineral deposit, in particular the iron ore. It is also a global biodiversity hotspot for subterranean fauna. So this location is on Western Australia. Isa na sa mga best location or mga best sample sa iron ore deposits. Dagan kini mga fossil fuels diri nga lugar, ug also isa din siya sa mga habitats sa mga cyanobacteria in ancient times. So nearly all the Earth's iron comes from the ore deposits in rocks formed more than 1.8 billion years ago. This began forming when the first organism capable of photosynthesis began releasing oxygen into the world's oceans, which combined with the dissolved iron to produce hematite and magnetite. Evidences of life during the Archean period. So 2.7 billion years ago, a bluish-green microscopic organism called cyanobacteria flourished in Earth's ocean. They made gaseous or free oxygen from carbon dioxide, water, and sunlight, a process called photosynthesis. As cyanobacteria created more free oxygen, the amount of oxygen in the atmosphere reached 1% of today's level, which is 21%. So ang cyanobacteria isa sa mga first nga mga microorganisms na capable of photosynthesis, in which kailangan nila ang sunlight, the carbon dioxide, and the water. So the cyanobacteria produces or releases oxygen into the oceans or the seafloor, and then that's why the life on the oceans are already bloomed. And when the oceans or the seafloor nga na-reach na niya ang maximum sa iyang oxygen, the cyanobacteria began releasing the oxygen into the Earth's atmosphere.